Welcome back to our series on statistical methods. I'm Mark Ledbetter. This is lecture 14. We are in part 7 of chapter 3, talking about one-way ANOVA. Previously, we talked about performing the ANOVA, verifying the assumptions, and now we're discussing what we do once we reject the null hypothesis. After we have verified that the assumptions are met, and if we see that the treatment effects are in fact significant, then we know that the model the model Yij equal mu I plus epsilon Ij is the right model, and that would tell us that these are not all the same. If we fail to reject the null, we end up with the model mu plus epsilon Ij, which is just a constant function across x, which is not very interesting. So it may be good, it may be bad, it depends on what you're testing. So we talked about last time estimating the population parameters, specifically mu I, and calculating their confidence intervals. We also talked about a difference in the treatment means. These were pairwise that we talked about. We talked about 3 different methods. We talked about using unadjusted, which was the not adjusting for the experiment-wise error, which was the Fisher LSD method. We only control alpha for the pairwise, each pair of means. Then we talked about the Bonferroni method that adjusted for the experiment-wise error in a conservative manner by dividing by R, the number of different pairwise comparisons we wanted to make. And then we talked about Tukey's method that would also adjust, but in a different way. And Tukey's method falls in between the more liberal Fisher LSD method and the more conservative Bonferroni method. Okay, so now we're going to talk about contrast. All right, before we do that, let's talk about, before we define contrast, let's talk about the overall picture. These are useful for pre-planned comparisons. Again, if you if there are studies that have been done previously and you're repeating that study, say, on a different segment of the population or adding something to it, then you should know, based on those other studies, which contrast or which comparisons you want to make after the test is done based on previous experiments. But if this is the first time that you're doing something or you don't have the results from anyone else, you're going to be doing exploratory testing, and you won't necessarily know what it is that you should compare ahead of time. You'll have to examine the data prior to doing that. Comparing the data is called data snooping. And some of the methods that we've talked about don't work well if you do data snooping. So we're going to talk about Sheffey's method that allows us to use data snooping and still controls our experiment-wise error. But first we're going to talk about some other things. And we need to talk about why data snooping is bad. So in general, when I look at data, and anyone else, if I look at the means and I plot the box plots, that's data snooping, okay? I look at before I do the test, I look at the box plots to see which means look like they're higher or lower than the others or different than the others. And then I say, wow, I'm really interested in the difference between the 3rd and 4th levels of the of our wafer etching thing, where we had the 3rd level, mu3 corresponds to power of 200, and mu4 corresponds to a power level of 220 watts. And I say, well, I'm really interested in those. Or maybe I want the least amount of power possible, so I'm interested in the difference between mu1 and mu2. Okay? So that may be, I may know that ahead of time, that I want to see if there's a difference between the lowest 2 levels of power. So increasing from 160 to 180 is the least additional amount of power I have to use. Or Maybe I'm interested in the difference between mu1 and mu4. If there's no difference between those two, I can use the lowest power level and get away with this. Okay, but looking at what we had, we saw that from the box plots that as we increased the power, the etch rate increased. So it looks like we're going to reject our hypotheses, and in fact, we did when we ran the ANOVA. So with that, I may say I want to look at the 1 and 4 because it's the biggest difference, okay? And I may choose something else where there's a big difference, like 1 and 3 or 2 and 4. And so with that, I'm going to choose those bigger differences to investigate maybe, depending on what I'm trying to do. And if I do this, not just for this experiment, but for all experiments, then in general, if I will get to an experiment where maybe there's a difference between the means, but maybe they're not significant, but I can't tell that until I run these tests. And so I will choose the differences that are naturally, I'll just choose the differences that are larger to test. And when these larger differences are consistently chosen, we're going to end up inflating the type 1 error because it's there's an unusually high percentage of the selected comparisons overall where the observed differences are only the result of random error. And so that is what causes the inflation in the type 1 error, is that we're looking at these tests and the differences may just be a result of random error. What do I mean by that? The random sample that you take, it may be that the random sample that you've taken is a extreme sample. It doesn't represent the population very well. And so if that's the case, then these differences are a result of that randomness of the sample or random error, and they really aren't a big difference. So you're going to reject the null hypothesis more often than you should in that case. So we have to be careful with this. All right, so let's start talking about contrast and defining them. It's considered a multiple comparison, and they are linear combinations of parameters. In our case, it's going to be treatment means. And so we're going to use the Greek letter, the capital letter gamma here, and this is gamma. If you remember from our mathematical statistics and probability theory courses, gamma is, there is a gamma function, and so we used this symbol before, so hopefully it won't be new to you. It looks like part of a T, almost like half of a T, capital T. And so please don't be intimidated by this notation. It is a linear combination, in this case, of our treatment means. What does this represent? This would represent C1 mu1 plus C2 mu2 plus, and so forth, to CA mu A. Okay. And this is a very important restriction where it says that, don't know how that happened, but it says that the sum of the coefficients have to add up to 0. So this would mean that C1 plus C2 plus up to CA, those are equal to 0. That means some of these have to be negative and some have to be positive. That's why it's called a contrast, because there's some positives and then we subtract off some of the negatives. So we add the means and we subtract some different means, so we're seeing a difference between the two groupings of means, those that are positive and those that are negative. Now, our null hypothesis, when we want to test this, is we want to test whether gamma is equal to 0 or not. Well, we never write gamma equals 0 as our null hypothesis. Please do not do that. That is not what we do. We write it out like I've written it here. So this is our null, and this is equivalent to gamma not equal to 0, but again, don't write it that way. Write it as the linear combination so people can understand what you're saying. And in fact, you'll see that we write it this way. This is equivalent to mu3 equals mu4, but we're not going to really write it that way because we want to view it as a contrast. We want people to understand that it's a contrast. And so here we have mu3 minus mu4. That's a contrast. So what's the coefficients of mu? 1? It's going to be 0. How about mu 2? It's 0 because they're not in here. Okay. And we'll do that a little bit. All right, so here we have this is equal to mu 3 plus mu 4. And so again, mu 1 isn't in here, so its coefficient must be 0. And mu 2's coefficient must be 0. And mu 3's coefficient will be 1, positive 1, because this is a positive. And then this is supposed to be a negative, so I'll make that a negative. And so then mu 4, its coefficient, C4, is negative 1. And so then I have 0 plus 0 minus 1, or plus 1 minus 1, that's 0. So we've met our requirement that these add up to 0. Okay. Now, what if we're interested in the average of the first two levels versus the second two levels? So what we have is mu 1 plus mu 2 over 2 is equal to mu 3 plus mu 4 over 2. Well, I can multiply both sides by 2, and the 2's cancel out, and I'm left with mu 1 plus mu 2 is equal to mu 3 plus mu 4. Now I subtract these from both sides, gives me mu 1 plus mu 2 minus mu 3 minus mu 4 equals 0. And I have a contrast, and that is what we have here, our contrast. So C1 is 1, C2 is positive 1, again, that's the coefficient here, and then negative 1 for C3 and negative 1 for C4, and again, sum of Ci equals 1 plus 1 minus 1 minus 1 equals 0. So, when you add a negative, it's the same as subtracting. I hope you see what I'm doing here. Okay. So we want to come up with a method for testing contrast. How are we going to do that? So we first need an estimate for gamma. So C is our estimate for gamma. And in that, we're still using Ci, but here we're using yi.bar, which is the estimate of mu I. So the only thing that gets changed is the mu I gets estimated by yi.bar. Okay? Now, I want you to note that the expected value of C is equal to E of the sum of Ci yi.bar. And the expectation of the sum is the sum of the expectation, so I can bring E of Ci yi.bar. And then Ci is a constant, so this is equal to the sum of Ci E of yi.bar. And the expected value of yi.bar is mu I. So this is the sum of Ci mu I, which is equal to gamma. So the expected value of C is equal to gamma. Now let's do the same thing with the variance. I want to remind you that the variance of x bar is equal to sigma squared over n. So the variance of yi dot bar is equal to sigma squared over n, because remember that we said that for all levels of I, we have a constant variance, or the same variance, sigma squared. Okay? So the variance of C is the variance of the sum of CIYI dot bar. And because these are independent, the yi dot bars, then this becomes the sum of the variances, CIYI dot bar. Because if they weren't independent, then we'd have a bunch of covariances in here. But the covariances are 0 because they're independent. And then when I take the variance of a constant times my random variable, I square the constant and bring it outside of the variance. So I'm ending up with the sum of CI squared, variance of yi dot bar. And remember that the variance of for any level of I is going to be sigma squared. And then so the variance of the mean is sigma squared over n. Ci squared, sigma squared over n. And I can rewrite this as sigma squared over n, sum of, okay, so this is C, so yi bar, this is going to be, I'm sorry, these are hats, because there's not mu I, they're yi dot bar. So these are all hats over the sigma. And it doesn't have any index, so I can bring it outside the summation, and I'm left with the sum of Ci squared, I equals 1 to A. And this is equal to the MSE. If you remember, sigma hat squared was MSE over n sum of Ci squared, I equals 1 to A. That is the variance of C. Okay. So now we want to do a t-test. So if we know, so what happens is we've got T naught, and T naught, we use C on the top, so we're going to use the sum from I equals 1 to A of Ci yi dot bar, and then to divide by its standard error, the standard error of this thing. So we found the variance. So the standard error of this estimate, the variance of the estimate, the standard error is the square root of this. So we take the square root of MSE over n times the sum of Ci squared. And you don't have to put the I equals 1 to A in this case. We know that, but I'm going to just to be thorough. Then this has a T with T distribution with n minus A degrees of freedom. Remember, the degrees of freedom of the error is n minus A, and that's why this is the degrees of freedom, because we have the MSE right there. And so the degrees of freedom of the error, or SSE, is n minus A. Okay. So our rejection region is that the absolute value of T naught is greater than T alpha over 2 n minus A. Now again, this is for an individual contrast, not a group of contrast, just an individual contrast. So once we start doing multiple contrast, then we need to adjust for the experiment-wise error. Okay. Now this was method number 1, is a t-test. Method number 2 is an f-test. And so what we can do is we can take the mean square differences of the contrast, which is going to be the sum of squares of the contrast divided by its degrees of freedom, which is 1. And then we can take the sum of squares error divided by its degrees of freedom. That's what the MSE is. And so we need to define what SSC is. And it turns out that SSC is the sum of Ci yi dot bar, quantity squared. Remember that this is a contrast, so there's negatives and positives in here, and so the differences are the squared of this contrast. That turns out to be a sum of squares difference, because we've got some C's that are positive and some C's that are negative, because the sum of Ci has to be 0. The only way that can happen is all of them be 0, which is very uninteresting, or some are positive and some are negative. And then divided by everything except sigma squared. So the variance, so this is the degrees of freedom, well, not the degrees of freedom, this is the the variance minus or without the MSE in there. So you can see that this is almost the same as this, just divide out the MSE. Okay? And we talked about this being a variation, so we have this standardized form of SSC. So when we divide SSC by MSE, we end up with this equation here for F naught. Okay? And this is going to equal T naught squared, because we have 1 degree of freedom on the top. Okay? And, well, I shouldn't draw it that way. We had 1 degree of freedom here. Okay? So how did we get this expression? So we took SSC, which is the sum of Ci yi dot bar, quantity squared, and it's divided by 1 over n, sum of Ci squared. And so that is the fraction on the top, and it's divided by MSE. So if we invert and multiply, we end up with the sum of Ci yi dot bar, quantity squared, over MSE over n times sum of Ci squared, okay, which is our f. And so we have 1 degree of freedom in the numerator, the n minus a in the denominator, in this case, the degrees of freedom of the error. So that's an f statistic with 1 degree of freedom in the numerator and something else in the denominator. That means it's a square of a t naught, or square of t naught, and t naught has a t with DFE degrees of freedom. And so 1 for the numerator, and whatever t has as its degree of freedom, that's the degrees of freedom in the denominator. All right, so you should remember that from our transformations that we talked about in chapter 2. All right, so for one-way ANOVA, F naught has an F with 1 degree of freedom in the numerator and a F distribution, I should say. 1 degree of freedom in the numerator, n minus a degrees of freedom in the denominator, because for a one-way ANOVA, that's the degrees of freedom of error. So you can see that I'm setting this up to be expanded to two-way, three-way, etc., because I'm saying that we have the degrees of freedom error, but in the one-way, that's n minus a. In the two-way, that's something different. And the critical region will be when the F naught is greater than F sub alpha, 1 degree of freedom numerator, n minus a degrees of freedom in the denominator. So that's our rejection region, or critical region. Okay? And so to make a confidence interval for this with 1 minus alpha, percent confidence interval, we will take C plus or minus the critical value, which is the T, alpha over 2, n minus a degrees of freedom, square root of our standard error of C, which is the MSE over n times the sum of the constant squared. And this is if there's equal sample sizes, and we should have sum of Ci equals 0. If we have unequal sample sizes, then we have to make this an Ni, and that means that it can't be outside of the summation. And so we have Ci squared over Ni. Since they both have indexes of I, they have to be summed across there. And then we would have a new restriction, a different restriction, where NiCi equals 0. If this was n, then n doesn't have an index of c. If they're all equal, it comes out here and we have n sum of Ci equals 0. That's only true when the sum of Ci is equal to 0. Okay? So we have the same requirement for both, but when we have constant or equal sample sizes, then this n, the Ni becomes n, and n can be pulled outside of the summation and becomes unimportant as far as making the sum 0. Okay? So this is basically saying that the weighted coefficients weighted by the sample size have to equal 0. Okay? Standardized contrast. It's useful to have several contrasts of interest be on the same scale, so have the same variance. So to do that, we divide by the variance. So, the coefficients of the variance. We want the variance of C to equal sigma squared, okay, or sigma hat squared, I should say. So it'd be sigma squared. So the variance would be sigma squared. Okay, the expected, the theoretical variance of C should equal sigma squared to make it a unbiased estimator. So what we do is we take Ci and we divide by everything except MSE, because we're getting rid of, we're going to keep sigma squared in this. So we take it and divide by the square root of the variance, but dividing out sigma squared and so no sigma squared here. Okay, so no sigma hat or MSE there. And so it's 1 over n sum of Ci squared. This is for, of course, balanced, so equal sample sizes. For unequal sample sizes, then we divide by the square root of the sum of Ci squared over Ni, that sum. And This means if we take the variance of these new CI stars or asterisks, that we will get sigma squared as the variance of that. All right? Now, so that's standardized. Now, orthogonal contrast. So if we have orthogonal contrast, two orthogonal contrast, and let's say the coefficients of the first one is Ci, the coefficients of the second one is Di, they're orthogonal if and only if, for balanced design, the sum of Ci times Di. So for I equals 1, that'd be C1 D1. We keep multiplying those and adding them up, like C1 D1 plus C2 D2 plus up to CA DA. That has to be equal to 0. Now, if they have unbalanced designs, then we have to do N1 C1 D1 plus N2 C2 D2 up to NA CA DA. That has to be equal to 0. So again, it has to be weighted by the sample sizes if the sample sizes are not equal. So for A treatment levels, there are A minus 1 orthogonal or independent contrasts that will partition the sum of squares of treatment. And so it's going to partition it into A minus 1 independent components. Okay? And so each component will have 1 degree of freedom, because if there's A minus 1 of them, then I add up 1, A minus 1 times, I get A minus 1, which is the degrees of freedom for the treatment effect. So a partition is where we have non-overlapping portions that make up the whole. So they're all adjacent, they all touch each other, they touch each other in such a way, or that they have common boundaries, I should say. So there's some common boundaries there, and none of them overlap. So you don't see the boundary going down something like that and muddling it up. It's each of the partitions or the portions of the partition are separate. So they do not have any overlap. They are disjoint to each other. Okay, or mutually exclusive. All right, so this is what we do. So when we perform tests on orthogonal contrast, they are independent. The results are independent. That is very nice. So we like to do that. So here's an example. Let's say that we have 3 treatments, and let's say that level 1 is a control, and we have an equal sample sizes, Ni is equal to N for all I. That's what that symbol means, for all. It could also mean for each, but in this case, for all works well. And then levels 2 and 3 are different than the control. So they're different treatments or different treatment levels. So we need the sum of Ci Di equal to 0. So we need to choose our coefficients. So I've drawn this so that we have C and the different treatment levels 1, 2, and 3. So if treatment 1 is a control, we could let 1 equal 0, and then we need these to add up to 0, so we could say 1 and -1, or -1 and 1. Let's see, I want -1 and 1. And then here I could have -2, and then I could have 1 and 1. Does this work? So I have -2, 1, 1, and then 0, -1, 1. I multiply these matrices, and I get -2 times 0 plus 1 times -1 plus 1 times 1. So the first goes with the first, the second goes with the second, and the third goes with the third. That's what we're doing here, and this gives me 0 minus 1 plus 1 equals 0. So yes, I have an orthogonal, I have 2 orthogonal contrast. Okay, so C is my first contrast, D is my second, and they are orthogonal to each other. Okay. Table 9 provides coefficients for orthogonal contrast. So if you have more than 3 treatments or 3 levels, this is a real nice table to say here are the possibilities, all the possibilities for that. And I think it may go up to like 8. And so it's a very nice table to have. Now, Sheffey's method allows data snooping, which is really nice. I have to use that in most of what I've done, I had to use Sheffey's method because I have to do data snooping because I don't have a preconceived notion of what should be different based on the exploratory analysis in most cases. So the experimenters may not know in advance which contrast they wish to compare, so they may be interested in more than A-1 possible comparisons. So in many of the exploratory experiments, like I said, these comparisons of interest are not known until after preliminary exploration of the data or data snooping. So what Sheffey's method does is it controls the type 1 error so that it's never more than, so it's less than or equal to, or at most alpha for any possible comparisons. Suppose that we want to determine a set of M different contrast of the treatment means. So what we could do is, I'm going to zoom in, we could give 2 indices to C. We still only have the 1 indice for the treatment means. But now we could have, for the first contrast, we'd have C1, let's say for U equals 1, C11 could be a number, and C21 would be a number. C11 mu 1 plus C21 mu 2 plus up to A1 mu A. And then for the second one, where U is equal to 2, see we have U equals 1 to N, we'd have C12, so that could be a different coefficient than C11, but times mu 1 plus C22 mu 2 plus CA2 mu A. So that would be our different, that's how we're doing the different contrast. So they all deal with combinations of mu 1 to mu A. Some of these C's may be 0, the constants, but or coefficients, but we can define them, okay? So for C sub U, we would call it whatever value of U, like C1 is equal to C11 Y1 dot bar plus C21 Y2 dot bar up to CA1 YA dot bar, okay? And so this would be C1. So CU stands for the U, what value you're going to put in for the U everywhere, okay? And then again, U can go from 1 to N. The standard error of S sub C sub U is going to be the square root of the MSE. And this is if we don't have equal sample sizes. So remember, it was for equal sample sizes, it was MSE over N times the sum of CI squared. And for unequal sample sizes, it was the square root of MSE times the sum of CI squared over NI. And so that's what we have. And this is a more general thing, so we can simplify this if all the n's are equal. If ni's are all equal, then the n just pops out to over here, okay? So sometimes we write the more general form, which is a little messier, but it applies to all the situations. Okay, so that would be the standard error. And then the critical value is going to be the standard error times, so this would be S sub C sub U, A minus 1 times an F statistic, F sub alpha, A minus 1 degrees of freedom in the numerator, N minus A in the denominator, and so we don't need a special table for S sub alpha U. We calculate it using S sub C sub U, which we can calculate from the data, and then A minus 1, the square root of A minus 1 times this F statistic we can look up from the F table. And so our hypothesis test is that gamma sub mu is equal to 0 versus gamma sub mu is not equal to 0. And so again, we wouldn't write it this way. We would write it as C1 U Y1 dot bar plus C2 U Y2 dot bar plus CAU YA dot bar equals 0, and then same thing, not equal to 0. Okay, so don't write it like that. Reject H naught if the absolute value of CU, Cu, is greater than S sub alpha U, so that is this critical value here, okay? So that would be our rejection region. Now let's talk about simultaneous Ci. So here is so we're going to have multiple confidence intervals for these contrast. And so remember that a confidence interval can be written like this. But that implies that gamma sub U is actually in there, but it doesn't have to be. In fact, when we calculate confidence intervals, if you remember, if it's a 95% confidence interval, then 95% of the time the true parameter, in this case gamma sub U, would be in the confidence interval, and then 5% of the time it would actually not be in the interval. So the gamma sub U could be anywhere in the interval, close to one end or the other. It doesn't matter as long as it's in there. Okay? Then it would be true. The other way to write it is Cu minus S sub alpha U, comma, Cu plus S sub alpha U as a interval. And again, the probability that all U of the confidence intervals are true simultaneously is at least 1 minus alpha using Sheffey's method. Okay, so let's look at an example. Unfortunately, I didn't do an example in this video of Sheffey's method, but I can show you the others, and then when we do the code next time, we'll make sure that we include Sheffey's method in the code. So this is copied from the output from the code. So we have the first contrast is that mu3 minus mu4 equals 0 versus it's not. Here C1 is 1, C3 is 1, and C4 is negative 1. C1 equals 0, C2 equals 0. So I need to correct that. We also want to check if the mean of the lower powers are equal to the means of the higher powers. So we've got this, but I would rewrite this as a contrast. So mu1 plus mu2 minus mu3 minus mu4. And we have to define our contrast in the code below. What happened to my code? Uh-oh. Okay. So I forgot to put the code. So what we did was we set C1 was equal to C, and this would be 0, 0, 1, negative 1. C2 is equal to C of 1, 1, negative 1, negative 1. Okay? And then we also were interested in, and I don't have that here, we want H naught mu1 minus mu2 equals 0 versus H1 that mu1 minus mu2 is not equal to 0. So C3 is going to equal C of 1, negative 1, 0, 0. And so we define this as our contrast, C1, C2, C3, and then we create this matrix called cont list, and we say it's a list of mu3 1 is equal to C1, mu1 2 minus mu3 4, it's really an underscore, is C2, and mu1 underscore mu2 is C3. Okay. Then we set least square equal to the LS means of model 0. And model 0 was an analysis of variance with the H rate. CH rate was power, and data equals Y1. So that was our model 0. Okay? And so we run this, and then we have contrast 1. We use the contrast function of least square and cont list, and the adjustment is the Bonferroni. We can also use the CDAC. And then if we do the contrast, what this gives us is the test. Okay? We could use these, we could then pull this information out and create the confidence intervals, but this doesn't do it for us. Okay? But this does perform the test, and it gives us the values here. The p-values. And so I've written up, I won't read this to you, I've written up the hypothesis test for each one of these. So please read over this and make sure that you understand this is how we're going to write it up, and you can modify that code in the code file that I have. Now, all three of these contrasts are significant. So since they are significant with this test, we can now calculate their confidence intervals. And what we're going to do here is the unadjusted confidence intervals. So what I've done is I've used alpha.o, which is just 0.05. So I have not adjusted for the experiment-wise error. And so here I have, this is going to be 3, or actually 4 minus 3, so I shouldn't say 3 minus 4. This should really be 4 minus 3 because it's positive, okay? And 4 was greater than this. And this is really the negative because I've got, so these are actually the opposite of what I meant for it to do. So why did it do that? That's interesting. But the difference between these two, you'll notice this confidence interval does not contain 0. Neither does this one nor this one. And 11's a little ways away, 49's even more, and 130's even more, even further away. Okay, so we can say that looking at these confidence intervals that mu 3 and 4 are actually on average 74.2, whatever that unit is for etch rate, greater than mu 1 plus mu 2. Okay. Now, we can calculate the contrast for all three, or the CIs for all three contrasts with the Bonferroni adjusted probabilities. Here I'm using alpha.r, 1 minus alpha.r divided by 2. So alpha.r was defined as alpha dot 0 divided by r, and r was equal to, here it should be equal to 3. Okay. And when we do this, we get the this confidence interval for the difference for the first contrast and the second contrast and the third contrast. Notice that this, for up here, we had 11, and now we have 1. Here we have 39, which is much closer to 0 than 49. So these Bonferroni intervals are much larger than the unadjusted intervals. Okay, so next time we'll take a look at the Chef's method, those results in the code. So if you have questions, please come to virtual office hours. If you can't wait, then by all means email me, and please take care of yourself and stay safe, because we want to see you next time.